Okay, so on this lesson, we're now looking at work, power, and energy calculations. So the first thing, like I said, this definition of work, you might want to know it because the formula will be there, and you find it also in the exam, in this exam formula sheet. Sometimes it might not be there, but it's fine, right? I mean, you'd have practiced these things. So the first important thing is that they don't just they don't provide displacement when it comes to this particular section. They can provide displacement in the projectile motion, but here, nope. In rare cases, they don't usually give you that. So you have to find it using one of these two equations that are here. The displacement equations from equations of motion. That is the first thing. You need to make sure that when you look into this particular section, well, you are really aware that the unit going to be provided with displacement. The formula for power, it can be that, or it can be that, right? So you can use work over time, and since we know that from the top here, we know that work is F times S, right? Force times displacement. You can also say force times displacement over time. Furthermore, if you look at S over T there, it is velocity, right? So that is what makes us say power is equal to Ft times V. So that is it there. Then I really had to emphasize here that please, when you're going to be calculating the maximum power, do not use the net force, do not use the rolling resistance. You need to use the tractive effort, Ft. That is how you determine the maximum power. Alright, then the other thing that we also discuss when it comes to this particular section is sometimes you might be required to calculate the kinetic energy, and sometimes it might be, well, in rare cases though, but maybe N2, right? That is where you'll be required to define kinetic or potential energy. Here we are very much concerned about the calculations. So that's the thing. Then here's another important thing when it comes to the incline, because of course at N2 we usually talk about horizontal movement, and vertical movement. And the vertical movement, that is where we can talk about the potential energy. And here we can also find ourselves having a vehicle that is moving along the slope or an incline, and then boom, they would want you to calculate the potential energy there, determine their height, because what they'll give you is the displacement and height are not really the same thing. So you need to determine the vertical height. So that is to say, S for displacement, sine theta. You need to appreciate that pretty well. While the laws of conservation of energy, the equations most importantly, are the things that we need to be concerned about. Please appreciate that it is potential energy plus kinetic energy. Then at another point, the second point, you have potential energy, kinetic energy, as well as the energy loss, and that is rolling resistance or the rolling force times the displacement. So now that it's like that, it means that mass will be very much necessary in these calculations, because if you look at most of the times we usually exclude this part, because usually these items will be just moving vertically. Here we are very much concerned about vehicles more than just imaginary objects. So if it was like that, without we were just going to ignore or cancel the M, but here we need to make sure that we include it in the calculations. All right. So I put about 3 or 4 checkpoints. Here's the first one. Please understand that when the car coasts down an incline, if it's moving down, it means that if they mention that particular word coasting, it means that it is disengaged and there is no forward force, or the tractive effort is not there. The vehicle is just, I don't know, it's just rolling like a bottle of water that is coming down the mountain, something like that. And the only force that will be doing work there is the parallel component of gravity. That is Fg parallel. I think we once mentioned that. So that is the thing that will be doing much of the work here. It is the one that will be jimming backspace. Alright, so the parallel component of gravity is the one that will be. So please understand that this word means that the item is disengaged. Alright, here's the other checkpoint. We are saying if you are asked to calculate the work done by the engine and the work done against the rolling resistance, we do not want to mix these, right? Work done by the engine, it is the tractive. Remember, the forward force comes from the engine. And then work done against resistance, it is the rolling force times the very same displacement. Then we also need to calculate mechanical efficiency, eta. If you want to calculate this one, appreciate that you can divide it by 0.8. And the other thing is you might divide or multiply. You need to be very careful as to what exactly is the question asking you. But you can appreciate that efficiency eta is equal to, sometimes I tell my students to call it Popeye, like PO, like for output power, then PI for input power. Don't confuse the two. Sometimes you won't find these formulas in the formula sheet. So efficiency is equal to Popeye, then don't forget to say times 100 anyway. So anything else you can just substitute into the original formula and then substitute the items that you have. In as much as this is something that you might do, but maybe memorizing can be boring, So I just appreciate this first formula here, which I called eta equal to Popeye, something like that. Then you will be fine. So, like I said, there are 2 examples that I put here, of which the second one, I would want you to give it a try. So here's the thing. Let's look at a situation. Let's look at the situation here. We're having a transport vehicle with mass 6 tons and it is accelerating uniformly from rest on a horizontal road until it reaches a velocity of 72 kilometers per hour in 15 seconds. And the constant rolling resistance is 200 newtons per ton. Then the efficiency is 85%. Then they ask you to calculate the distance covered during the acceleration. Distance. Then they say the tractive effort and the work done by the engine over the 15-second period, and the maximum input power that is required by the motor at the instant it reaches 72 kilometers per hour. Alright, so that is the question. So the first thing that you need to do is make sure that you list down your data, and your data has to be converted to SI units. So we have 6 tons, so 6 times 10 to the power of 3 from rest, so initial velocity is 0. Then the final velocity is 72, and I said you divide by 3.6, right, to get your meters per second. Then the time that we have is 15 seconds. Boom. The other thing, students usually take 200. I think I mentioned this in the previous presentation. Students have got a tendency of taking 200 and call it FR. No, wrong. Okay, that is incorrect. They said 200 newtons for every ton. How many do we have? 6. So you need to multiply by 6, right? So that you can get the exact thing. The other thing that we are given in the statement is the efficiency. Eta is 0.85, right? If you divide by 100 there. Alright, so gravitational force is 0 here because the item is moving along the horizontal surface. So the only forces that we're looking at, we have the rolling and the forward force. So that is what makes up the Ft. Alright, so that was the thing. So how do we determine the displacement? Boom, the equations of motion, right? So that's the thing. You can appreciate that particular formula, and boom, you get your displacement. And remember, you need to get your answers right from the top, because the wrong answer can lead you to the wrong and to the wrong, and you get a 0. Unfortunately, I don't know if they really care about positive marking, but anyway, I don't give students hopes of positive marking, you know. I just care about the right things from the beginning. Alright, so that is the thing. Then after that, the attractive effort, we are talking about Ft, right? And Ft, if you look at what I said, or is it today? Maybe it's not today, well, who knows? Ft, well, I didn't really mention it today. Yeah, so Ft, I mentioned it right now, right? When I was talking about, there it is, right? Fr and Fi. So we have the rolling, but we do not have Fi, right? So that is the thing. The reason we're calculating acceleration here, because Fi is equal to ma. And then boom. Therefore, your Ft is Fr plus Fi, and that's 9.2 kilonewtons. So that is the thing. And then the work done is the work done. They just said the work done, so we can appreciate the attractive effort. And that is the thing. Maximum, we need Ft as well, right? And velocity, I think I mentioned that. Then boom, that is the thing. So they said the maximum input, not the maximum output. My God, you know, students get overexcited when they see something that is familiar, and they tend to not to pay attention to what the question is asking. If you just calculate Ft using this and then end here, wrong, right? Because that is not the thing. Then after that, we also have efficiency, so we need to pay attention to the efficiency. So the real thing is that one. So if you use your Ft here and get the thing and then end there, you're gonna put yourself in some real problems. So that is what we want to avoid. Alright, so that being said and done, I want you to just take a screenshot of example 2. And oops, I didn't really put the marker locations. Yeah, I was going to time you, but I'm going to look at the time, then we give it a stop. So the thing is, that is the thing. I want you to try and answer example number 2 for now, if you do not have any other questions though. Do you have any questions?
No, I don't.
No questions. Great.